All right, so welcome everyone. Thanks for staying for the next iteration of the first breakouts in the conference. Well, if you weren't here in the morning earlier, my name is Adolfo García Veytia. People usually call me Puerco. I am working on a new startup that I created earlier this year called Carabiner Systems. Our mission is try to basically take all of the supply chain technologies out there and make them work and play along together really well. I maintain a bunch of the initiatives in the OpenSF, the technical initiatives, namely OpenVex and Protobam. I also collaborate with the open source project security baseline. I came onto the OpenSF via the Kubernetes world. I work on the Kubernetes release engineering team where we maintain all of the supply chain tooling that protects Kubernetes releases. All right, so this talk is about an example implementation of SLSA end-to-end. So earlier this year, a couple of months back, the SLSA project put out a call for examples of end-to-end SLSA implementations. And so the idea is, can you actually implement SLSA? And if you can implement SLSA, can you do it end-to-end? And we're going to see what that means in a little bit. So we answered. So my company is working on a project called AMPEL, a policy engine that I'll be going to be showing you. So this talk is about not necessarily referencing the SLSA end-to-end implementation, but what I want to show you is some of the advanced features in the policy engine that make this possible. I don't know, a quick show of hands. Who here is not familiar with what an attestation is? Perfect. That's what I was hoping for, so I can skip over these slides. So, all right, so AMPEL. So AMPEL is our flagship project. It's an open source policy engine. It got a name, and then it became an acronym looking for meaning. Right now, it stands an amazing multipurpose policy engine, NL. And then the idea of AMPEL is that it's a binary, but also can be used as a component to be embedded in every place that you need to perform verifications in the development lifecycle. So we're going to see some of these embedded use cases today, protecting a software build. So AMPEL works on policies as code. The way that these policies are structured is that they have a JSON frame that holds all of the policy pieces together. We also support HJSON, which I didn't know until I started working with larger JSON files. HJSON is like an extension to JSON that you can transpile to regular JSON. It allows you to have comments, which is really useful. And also strings in multi-line strings, so it's easy. We have a policy control tool that can transpile policies back and forth. And the three main parts of the policies are the metadata, which has information about the policy itself. Then we have the attester identity, so whenever you ingest an attestation, you define who is supposed to be signing that attestation. And finally, the tenets. And the tenets are the data in the attestation that we expect to be true. Policies can have more than one tenet, and you can and or them. So you can have, for example, alternatives or require each check to pass. The tenet code can be defined in more than one language. Right now, we only are shipping the cell common expression language runtime. So you write your policies in Cell. We're also experimenting with Rigo and with CDAR from Amazon to see if we can plug those in there. So this is basically what the very core of the tenet looks like. So if you have an attestation and you can look for a pass value, you can check, so this is just like checking for a pass value in an attestation in the attestation JSON, or checking if it complies with SLSA Source level 4. more useful is that policies can be tied together to security frameworks. So if you have a bunch of policies and you do an evaluation, you can translate those into results of a framework evaluation. So for example, we use this for the baseline, the open source security baseline in OpenSF. You have a bunch of policies, you pick those that check for your security implementation, and then it can tell you if you're complying with baseline or not. I did a talk a couple of months back, if you're interested, about baseline compliance with attestations. Now, more interesting than the policy itself is that you can use policy sets. A policy set is a collection of policies that you bring together, and then those are evaluated as a single unit. And what becomes really powerful about the policy set idea is that you can reference policies remotely. So you can reference the policies from an HTTP server or from a Git repository, and then bring them into your policy set. So that means we collectively can work, and we're already doing that, can work on a policy collection to evaluate common predicates. Like, for example, we have policies for SBOMs, for SLSA, for VEX, for vulnerability scanners. And then you just write your policy set and reference the code that someone else is maintaining in a repository. This is a screenshot from a couple of months back of the community policy repositories. Everything is open source, so ready to use. We have several examples that you can use. Now, let's talk about the project that we created for the SLSA end-to-end use case. So this is called the Free Toto project, and it's a combination, like a wordplay on Friday and in Toto, because, well, we all have been affected by the same problem. Deploying on Fridays is very, very bad, considered very bad by some. So bad that you can find any variation of the common memes talking about don't deploy on Friday. And not only that, there's like a whole set of merchandise that you can get, and some of it is actually peddled by very sexy models like this guy. So yeah, deploying on Fridays, not very well received by people, but this being the most pressing problem the humanity has faced, someone also started working on a project. So what the Free Toto project does is like I don't know, a little silly demo of a project that built something, and so we thought it was on theme. So Free Toto, what it does is that it produces an attestation that tells you if the software was built on Friday, so you can gate on it and then block if you want to. Like, this is actually real. If you want to actually block deployments on Friday, you can download it and use it. But anyway, so the important part is this one. So this is the pipeline that builds the Free Toto binaries, right? So it's very simple. It starts with pulling a commit from a repository, and then it uses a builder image, a container image from Go, to build the project. Before doing the build, it runs some metadata, like it executes, like runs a test, the project test. We'll see the metadata that we build. Then runs the build, runs the release process where it publishes the binary for consumption. Now, obviously, when you want to secure this release process, you want to gate on each of these phases to ensure that things are protected. And why? Well, when you're running the metadata, it involves creating, running tools and processes on your code. So if the code is not secure, or if you're running it on a builder image that has not been verified, it can introduce security problems, as you may be running some other third-party code that may attack you, for example. And then, same thing for the build. You want to make sure that the metadata complies with what you're expecting and then releasing. But the most important part is that all of this protection and security guarantees needs to be transferred to the user, because the one that actually needs to be protected is the user. I mean, your systems are also important to protect, but the most important part is the person using your systems. And the way we are going to be doing this is that we are going to be collecting information across the software lifecycle. So each of the processes is going to give us information that we'll be collecting, and then in the end, we're going to be able to evaluate that information from the user's perspective. And to do that, we're going to be gating each of the processes with AMPEL policies along the way. So if you refer to the blog post that I showed in the beginning, all of this is obviously open sourced, and you can take a look at the policies and the implementation. So through each phase, I made a mini map of the build process down there that we can refer to see where we are. So in the first one is the source code. So what do we mean when we protect the source? So SLSA has, most people are familiar with the SLSA build track, but it also has a new SLSA source track, which is coming out, the SLSA 1.2 draft. Second draft was released today, so before the end of the year, we should have the final SLSA 1.2 specification, which includes the source track. And what we mean is whenever you have your revision history, what you want to prevent is third parties injecting bad commits into your revision, because they can do all sorts of damage from that point, because you assume the code to be trusted. So SLSA source track, what it does is that every time a revision lands in your repository, you generate a provenance attestation describing the conditions of the version control system and the security checks that it has enabled. So whenever you push a new commit, you generate new attestations, and that guarantees that you know you're protected, that in all of the revisions that landed in the branch in the past had those guarantees in place. So the way that we do it is that we run a policy. So this is a screenshot of the workflow that we published for the example. And the important parts here are, so it's a reusable action. So we have this action that you can reuse in your project. It's simplified for the presentation, but basically you can see that the subject that we're going to be verifying is the commit SHA. Then the policy that we're pulling from the community repository that checks SLSA level 1. Actually, SLSA level 2 and 3 are easy to achieve, but since this is a repo for demos that I keep pushing data, it's only on level 1. Then you specify a collector, and the collector specifies where am I getting the attestations from. In this case, the SLSA source tooling embeds the attestation in the Git repository in Git notes, so we pointed to there. And finally, the signer identity that the policy will be looking for. If you see the signer identity, it's a SIG-star identity that specifies that we will be looking for the attestation to be signed by the actions repository, because the action runs in the SLSA repository from the main branch. So that's the first one. This is a deeper look at the policy on what it looks like. So at the top, we have the metadata, and then below the tenets. The tenets, this is kind of a basic one, so that's why I chose to showcase it. Like, it looks for a predicate, a VSA, a verification summary attestation, and then it has a code. It defines some outputs, so you can pre-extract data and then run the policy on the outputs. So that the code itself becomes easier. And having outputs also has the benefit that it exposes, in the evaluation results, you can read the outputs, and so you can chain and do other things with them. And finally, the messages that will appear to the user when they run the attestation. Next, the next is we use a Go builder, and we verify it. So for the example, I'm using a container image from a sponsor company of this conference that produces secure container images that come loaded with provenance attestations. And the policy, what it does is that it verifies the 3 requirements specified in the SLSA spec. So we check for the builder identity, the source repository, the build type, so to make sure that they are what's expected. We run the verification, then produce a signed VSA that we keep for later verification. So at this point, I was going to, but I'm little late on time, so probably I'm gonna just keep that showing you the policy. But then we go into generating more data for our build. So at this stage, we're gonna generate an SBOM from the source, then a standard in total attestation with the test results, and finally, vulnerability scan and a bunch of OpenVex files. The project in that repository is consciously pulling in a vulnerable dependency that is not exploited in the code, so we can generate confidently, because it's all manual, VEX files from it. So the idea is you can write a policy, and so you need to consider this like one, and I'm gonna show you why. Because you generate the vulnerability report that has CVs in it, but then mute them with an OpenVex attestation. So now we run the build. And then before we run the build, we do an evaluation of everything we had until this point. So we check our extra metadata, we check the SBOM, we verify the test to ensure that they are passing and that there are no vulnerabilities present. And then we check the verification results from our two initial dependencies, from the source and from the builder. If everything checks out, then we execute the build, but only until then, until we have cryptographic proof that everything was passing. Regarding the vulnerability scan, it uses a feature in AMPEL called transformers. So the way transformers work is that these are compiled in modules into the policy engine that take a bunch of attestations and remix them and give you another attestation internally. So in this case, you run a security scan with OSV scanner, gives you vulnerabilities, and then you take in a bunch of VEX documents, it crosses them all together, and in the end, the policy engine, the attestation that gets exposed to the policy engine is only the vulnerability scan with all of the suppressed results from the VEX data. And then once we run the build, we also generate a build attestation for the free Toto build. And to do this, we use, the example uses the Tejolote attester that we wrote for Kubernetes. This is what generates the attestations in Kubernetes. So we have actions for this project that you can use and in your own project. And essentially what Tejolote does is that when the build runs, it observes GitHub actions from the outside and gives you as much information as it can in a provenance attestation. And then at this point, the workflow has its binaries internally in the runner, and we do a release pre-flight. And the release pre-flight is we ensure that everything before the build matches out, and we do some verifications on the provenance attestation that we're going to be using to protect the user. And this one uses, so this last part uses another more or less advanced feature of AMPEL, where we use what we call subject chaining. So subject chaining works like this. When you have a policy is, you have a policy code that looks for conditions in an attestation, and it's a one-to-one mapping. But sometimes you will have an attestation of another related artifact in the supply chain. So for example, you can have a binary, and then you need to chain it to your commit. And how you can, so the document that connects those two is a SLSA attestation, because you know the build point. So you change the subjects by specifying a selector that extracts data from one and converts the subject under evaluation to the second one. I hope that makes sense. I rehearsed like several ways of trying to explain that, and this is just for changing the one attestation, but where policy chaining, subject chaining becomes really, really powerful is when you have multiple subjects in a policy set. So in a policy set, you may start with a commit, and then you connect that to for something that has more dependencies, like an SBOM, right? So you can start with a commit, and then you generate the SBOM, and the SBOM has a list of dependencies, and that means that your policy applies to everything that was selected under the chaining selector. So this means that you can write a policy, ingest an SBOM, and then apply that same policy to all of the dependencies in a project, for example. And then you get the results for each of those. And so we're using that here to apply a single policy to our the initial dependencies listed in the SLSA attestation. And then, we finally do the user verification using the VSAs produced through all of this process. If you go to the repository, we have, I can show you, hopefully it's big enough. So we have, inside of this repository, we have all of the policies that you can check that can be used to run the verifications in your own machine. And we also have an example of the data that we're collecting as part of the build, which I think I have a few minutes so that I can show you. So to show you this, I'm gonna, Jason. So I'll use this utility that we released called bind. So bind, what it does is that it lets you work with attestations, bundles, lets you sign them and inspect them, push them to registries and all of that. So I'm gonna open the bundle from the FreeToto run so that you can see what's included. JSON-L. So these are all of the attestations produced in the bundle. So if you go to the FreeToto release page, you'll see all of the binaries and this file with all of the attestation bundles in them. So you can see everything that we produce during the run that gets published. So there's this is the source provenance from the GitHub repository. Then we have a VSA that verifying the image. Then this is the tag provenance because there's like the commit provenance, but also the tag provenance from the SLSA source track. Then we have a VSA verifying the dependencies. Hopefully, I mean, I cannot see the predicates here, but this is what I'm assuming. Then we have the SBOM here. Then another VSA from the dependencies. Then this is the provenance attestation for all of the binaries here. The OpenVex documents that we produced in the demo. And the vulnerability scan. The test results attestation. The verification summary for the user for each of the binaries. And the reason why, in the end, you would hand users a verification summary attestation is that, I mean, this is open source, so we don't have a problem of handing people all of the data. But sometimes you have internal data in your organization that cannot be shared to perform the verification. So the VSA is a way of telling your users, so I did previously verify this. You can trust me, and here's the proof of that signed by the software author or whatever. And yeah, so I don't think I have time to show the verification, but can show you after the conference happily if you want to. And yeah, so that's SLSA end-to-end. So that's the way we carry the trust from the source to the build to all of the metadata, verifications, and give it to the user to protect the run of the binaries. And finally, some links to the tools that we just showed. And yeah, if you have any questions, I'll be around all day. Happy to chat.